Chris in the chat says, thanks, Satya, you have a very average face.
Good one, good one. Let's get started. Welcome, everybody. Welcome to the OpenCV weekly webinar. And today we are going to present Eigen Faces, principal component analysis. We will learn about covariance matrices, and we'll start with the concept called variance. So it's today's, as I was saying before, today's webinar would be a little unpolished, but we will go over these concepts because our guests, some of our guests actually canceled in the last moment. And so we had to put together this webinar quickly. But I hope that with the material we have, it will still be a very, very interesting webinar for you. And feel free to ask questions. Let me begin with a question, Phil, right? Do I look like a celebrity, a Hollywood celebrity?
Well, I mean, obviously you're a very handsome man, Satya.
Well, you can see the sarcasm in his voice. He doesn't think like I look like a Hollywood celebrity. So let me share my screen. Let's see. Okay, so this is a list of these are some Hollywood celebrities. There are 200 of those.
I recognize some of them for sure.
Yeah, and some of them are not really Hollywood. Like we have people like he's a comedian, a British comedian, but they are on an average good-looking people. And by the end of this webinar, we want to show that if you take the best parts of these people, you could actually reconstruct my face, right? So this is the original face, which is a photograph of me. And if you take the best parts of these celebrities, you could actually reconstruct my face. So this image here has been constructed by combining the photos that we just saw in beautiful ways. Once you do that, you can reconstruct. It's not a perfect reconstruction, but you can see that it does pretty well.
It's like the opposite of this person does not exist. This person does exist.
That's right. This person does exist, but you can also do, what this person does not exist did. Let me bring up the code. Let me show you that you can actually do the same thing. So by the end of this webinar, we will actually be able to produce new faces. And this class of techniques, can you see my screen?
Yes.
Okay. So by the end of this webinar, we will be able to create new faces. And these are old techniques. These are classical computer vision techniques that are not deep learning based. When you look at something like GANs or this person does not exist.com, those images were created using deep learning, a class of techniques called GAN. But this image is considered, these are classical computer vision techniques. So here also we will be able to
I see you've got a little UI there too. That's interesting.
Yes. So, people will be able to get this code. Actually, I have the code. Phil, you can actually put it right there.
Yeah, I'll drop the link, the Learn OpenCV link.
Yeah, it's actually on GitHub. You can go to github.com/spmalik, learn OpenCV, and then Eigen Face is the one that we want, and you can link to that post, that code. And here, so by the end of this, we'll be able to show you this, it generates new faces. Obviously, it's not as sophisticated as the new techniques in GAN, but you will learn a lot about, how this thing works. Okay. So, but let's start from the very beginning, right? Let's start from the very basics. What is principal component analysis? What we need to know here are certain concepts like principal component analysis, eigenvalues, eigenvectors, etc. Right? So let's start with the concept of principal component analysis. Now, if you look at, let's say if you want to play 20 questions, right? Let's say you are a person living in the United States, and I give you a set of 20 questions, right? The first question is, these are political questions. So I'm going to ask you things like, do you support gun control, right? Or do you support women's right to abortion, etc.? And there are these 20 questions I can ask. And now think about the dimension of the space. There are 20 questions. Each question is binary, which means that it can be answered as a yes or no. So the dimension, it's a 20-dimensional space of questions. And the number of possibilities is basically 2 to the power 20, right? Because there are 20 questions, each question can be answered in 2 ways. I could do that, and you would imagine that, oh, if the data was evenly distributed, if the opinion of people was evenly distributed, you would get all of these possibilities would be present. But you'd be surprised that instead of these 20 questions, I could ask simply one question. And the question is, are you a Democrat or a Republican, right? And most of the time, I can answer all those questions based on this single question. So the 20-dimensional space of questions has been reduced to a single dimension, which doesn't capture all the nuances, but still it will give you the right answer a lot of times, right? So that's dimensionality reduction at its core.
Essentially, you're talking about compressing the data from multivariate into just one thing.
Yes, and the reason is that data has correlation, right? It's not like people are completely independent entities. Our opinions are very correlated, right? Suppose you are for gun control, there is also a good chance that you would be, pro. I always get confused about these nice terminologies they use. So you would be against, you would be for abortion, right? If you are for gun control. So those are just because we divide ourselves into these political, we support one side or the other, and our opinions are not completely independent. That's just the fact of life, right? So that doesn't just exist in human data. This kind of thing exists in a lot of natural data, where things are correlated with each other. The things that we think are uncorrelated. Another example would be things like, what is your height? Height and weight are correlated, right? They are not independent entities, but because it's finally boils down to mass. The person who has a higher height will also tend to have a higher weight, right? So data is correlated as what.
Yeah, bones weigh something.
Yeah. So next, the next concept we want to learn is the concept called variance, right? What is variance? What you're looking at here is 2-dimensional data. We have data in X and Y dimensions. And the red dots basically show the location of the data. And on the left-hand side, you could see that the data spreads more than the data on the right-hand side. The right-hand side is more compact. So we say that this data has lower variance, and this data has higher variance, right? It is spread. Now, you may, an important concept to learn in machine learning is that information is in the variance, right? You should note it down somewhere, that information is in the variance of the data. If there is no variance in the data, there is no information. And I'll show you with an example. So here, this is also 2-dimensional data, right? Because we have X and Y components for these data points. But Y is always the same. Y is always the same. So you can literally throw away Y completely and just rely on X, because Y has 0 variance. all the variance is in the X dimension, right? So information is, you can think about variance as information. You need to capture the variance to capture information. And the dimensions which have zero variance, you can remove them without much loss of data, right? So in this case, you can remove the Y dimension perfectly without losing any information, okay? And that's the crux of dimensionality reduction. So
I'm learning stuff already. I got to be honest with you, Satya. It's been about 20 years since I took a math class. So,
but feel free to interject, really, interrupt me and ask questions if you don't understand. Are you with me?
I'm with you so far. This is interesting.
And even the audience, please feel free to interrupt if you feel that a lot of people are having trouble understanding the concept. Mm-hmm. I will reiterate the concept, right?
Yes, I will be your voice audience. Okay. Let us know if anything's not clear.
All right. So how are we doing so far? Have people understood more or less? Okay.
So far, so good.
Yeah. So we have learned that, the information is in the variance, and variance simply means the spread of the data. Low variance means there is no change in data, and high variance means the data is, spread more. But we also care about the direction of variance. As we saw in the previous example, that the Y component had zero variance, and so it was not important. But most of the data is not nicely presented that way, right? Usually when you look at this data, it could be somewhat like this, right? There is some correlation in that direction, not in the X direction, not in the Y direction, but some arbitrary direction, right? And this is where principal component comes into play. So principal component, this line is called the principal component of the data. It is called the first principal component of the data. This is the direction along which the variance is maximum, right? And in the previous example, that direction was this. But in this example, this is the direction. The second principal component is the direction which is orthogonal to the first principal component and has the highest variance. In a two-dimensional data, we just have one direction, right? There is nothing to choose from. So we have the first principal component, and the second principal component is simply orthogonal to this data. Now, what happens in higher dimensional space, right? Let's look at this three-dimensional space. In 3 dimensions, you can see that we have this first principal component, which is along the direction of maximum variance. Along that, now you can imagine a plane which is orthogonal. Orthogonal just means perpendicular. So you can imagine a plane which is perpendicular to this line. And on that plane, if you project all the data, right, you smash all the data onto that plane, then it would start looking like 2 dimensions, right, like this. And on those 2 dimensions, you can again find the axis of maximum variance, and that would be our second principal component. And the axis which is orthogonal to that would be the third principal component, right? Is that clear?
I think so. Really, so part of what this is about maximizing the variance at every step.
Yes,
right?
we are trying to find the directions along which the variance is maximum. And the reason we are doing that is once we find all these directions, we will remove all the directions where the variance is smallest, right? And that way we can determine which data is useful, right? Which axes or which directions are useful, and we can remove all the axes with small variance and still keep the essence of the data. And that's how we are able to reduce the dimension, but still able to capture the essence of the data. Does that make sense?
Yeah. So in other words, what we're trying to do is almost simplify the data without losing any of the actual important information.
Yep. In fact, we are rotating the data in some sense. If you think about it, we are rotating the axis and we are basically rotating this XYZ space. and also scaling it, but think about it as rotation. So you're rotating so that the axes become aligned with the directions of maximum variance.
I see.
Yeah. And and don't worry about how it is being done, how it is being achieved. First, let's understand the concept, and the details, the mathematical details we can understand later, right? How exactly it is done. What we are trying to achieve is more important right now.
Makes sense.
Okay. So, okay. Now, before we move on to, I've already explained, how PCA leads to principal component analysis leads to dimensionality reduction. Basically, we throw away all the examples, all the dimensions where the variance is small, right? So before we move further, let's go over a concept called eigenvectors and eigenvalues of a matrix, right? Now, let's say we have this matrix, and don't worry about the numbers. It is some matrix that I have constructed. It is some random matrix. And I have a vector for this matrix. And this I have chosen carefully, right? It is not some random vector. It is actually a vector that I have chosen very carefully. And let's say, some gods of mathematics gave me this vector. So here's an interesting thing about this vector. When I multiply this matrix to this vector, I get some, unfortunately, there is this display problem, but anyways.
Thanks a lot, WordPress.
We have this, I just multiplied this matrix to the vector, and out pops the same vector, right? If I do some mathematical, jugglery, I can see that the same vector pops out with a scale, right? So AV is, the effect of this is basically scaling this vector, just scaling this vector. Typically what happens is that when you multiply a matrix to a vector, it scaling the vector, imagine the vector as a direction, right? Scaling just means that the vector has changed in that direction. But typically if you apply an arbitrary matrix to a vector, it's going to scale it, rotate it, do all kinds of transformations to it, right? It's a 3x3 transformation. It can move this vector in any way. But if it is the eigenvector of the matrix, then it only changes, along the direction of the vector, right? The vector is only scaled. So let me repeat it. So the eigenvector of a matrix is a vector which, when multiplied to the matrix, changes its magnitude only. The direction of the vector doesn't change. So A times V is lambda times AV, right? And we'll not go into how this thing is calculated for a matrix, because you can actually use a standard algebra package and find how this eigenvalue is calculated. That becomes slightly more complicated.
One quick question from the audience here about how do you know when you've done enough with the PCA? Like, how do you know when you've thrown enough data away or compressed it enough? How do you know when you've gone too far?
Well, that depends. That completely depends on your application, right? How much data you want to throw away completely depends on your application. And that's also where you have to be very careful, right? Sometimes you can have very wrong interpretation of the data because you threw away too much nuances, right? It also depends.
This is a little bit more art than science, I guess, is what
it is. It is more art than science, right? And sometimes you have other technical limitations. Sometimes you have this problem of you don't have enough processing power. So you need to reduce the dimension of data so that you can do some processing. You can get some answer instead of processing these. And here, the example, you may not completely appreciate how well dimensionality reduction works. But imagine you had 1 million the vector was millions of dimension, 1 million dimension, and you're able to reduce it to 20 dimension. For a 1 million dimension data, and there could be millions of points, right? Now imagine that you're trying to solve something, you have a matrix of data, which is million by million. You cannot load it in memory easily. You cannot do anything with it. But let's say you reduce the dimension to 20, then you have a much more manageable problem, right? So sometimes it is dictated by the technology you have at your disposal, the processing power, etc. But it's a very valid question. Sometimes when you throw away a lot of data, you can reach very wrong conclusions, right? Because the nuance has been removed.
Yeah, definitely.
So how do you calculate? So I'll go through the mechanical step of calculating the principal components of a data, right? So let's say you have this three-dimensional data, right? You have points in three-dimensional space. And usually, we will come to it. Any data you have, let's say you have an image, you can convert it into a vector, right? And that's, I like to say that mathematicians, they have done so much research in linear algebra that computer vision people and other people in other fields, all they want to do is take their problem and convert it into a problem that the mathematicians have already solved, right? So if you have an image, you somehow convert it into a vector, right? So your image becomes a vector in a space. Now just use all the tools that mathematicians have developed over centuries and your problem is solved, right? So when I talk about this data, right, you can think about it as an image also. Instead of XYZ 3 dimensions, you can imagine that it is a vector of which has been constructed from an image. I'll give you a small example. For example, if you have an image of a face and it is 2000 by 2000, another image of a face which is 1000 by 1000, you can scale them both to 100 by 100, simple scaling, right? So now you have a matrix which is 100 by 100, and then you can take the columns of that matrix and pull them together into one vector, right? So the 100 by 100 image can now be represented as a vector, which is 10,000 long. Does that make sense? And any image, any face image can be changed to that by, you change the size of it, you crop, you do something, you do some manipulation to the data so that it can be represented by a single vector of fixed length. Does that make sense? Right.
I think so.
Okay. So here for simplicity, we are just showing 3, right? That vector space is just 3 dimensions, but there are many data points that you have, okay? And these are represented as each data is one column in this, and there are endpoints, right? So this is your data matrix. Let's call it the data matrix. The second thing you have to do is you have to calculate the mean along each dimension. So along the X dimension, you calculate the mean, Y direction, Z direction, and you subtract the mean from every element of this data, okay? So this is how the mean is calculated. You just sum them up, divided by the number of elements, and you do the same thing. And now for every element, you're subtracting the mean of the data, right? From X, you're subtracting the X mean. From Y, you're subtracting the Y mean. And from Z, you're subtracting the mean Z. And this is a very common pre-processing done in a lot of computer vision, machine learning applications. You remove the mean of the data, right? So it's normalized. It's equal in, it spreads equally in the positive and the negative directions, right? That's what it is doing by subtracting the mean. And then you find the covariance matrix. Now, and you have to bear with me a little bit. So here, look at this matrix M. This is the mean subtracted data matrix. The covariance matrix is basically that matrix multiplied by its transpose. And if you remember from linear algebra, transpose of a matrix is simply rows and columns swapped, okay? So you get this thing called a covariance matrix. Now, why are we doing this kind of jugglery? Let me explain it using an example, right? What does this covariance matrix represent? and I'm showing it in 2 dimensions because it is actually easier to understand in 2 dimensions. So remember, we were talking about the variance. Information is in the variance of the data, right? And here you can see that the information is spread, evenly in both dimensions. It's like a circle, right? It's spread evenly in the X and Y dimensions. So the covariance matrix, if you look at the diagonals of the covariance matrix, that represents the variance along the X and Y directions. And these off-diagonal elements, they represent how the 2 dimensions are interacting with each other. Does that make sense, Phil? Okay.
I think so.
So now, let's say if you change the variance in 1 dimension, you will see that this element of the covariance matrix changes. It says that, oh, the variance in 1 dimension is more than the variance in the other dimension, right? But if you actually tilt the data, then they start becoming correlated, right? And you will start seeing these off-diagonal elements come into the covariance matrix. Okay. So, now, you can see that the covariance matrix, it's related to the shape of this data, right? From this matrix, how do I find this principal component, right? And it just so happens that the eigenvectors, so I told you about the eigenvectors and the eigenvalues, what they mean. If you take the eigenvectors of this covariance matrix, it corresponds, so eigenvector is a vector, right? So it corresponds to the principal component of this data, right? And which eigenvalue, the question is which eigenvector, right? And the eigenvector corresponding to the highest eigenvalue, right? When that lambda, you remember this, we had talked about here, this V is the eigenvector and lambda is the eigenvalue. So the eigenvector that corresponds to the highest eigenvalue, that is our principal component, right? So now you can calculate, right, along these dimensions that, oh, it's actually, this is the direction of maximum variance, and this is the direction, this is the second dimension, and so on and so forth, right? So that covers, that's what principal component analysis is. Given a data, we are able to find the principal components of the data. And just to summarize, let's see how much time we have. Okay, just to summarize, what we have done is we first arranged the data into a data matrix, right, where each column corresponded to 1 data point. Then we took the mean along the X, Y, and Z directions, and then we subtracted the mean off, and we constructed the covariance matrix. And we found the eigenvalues and eigenvectors of this covariance matrix. And those give us the principal components, right? Those give us the principal components. The thing that I have left out is how do you calculate the eigenvalues and eigenvectors of a matrix, which, I mean, if you, practically speaking, you just use something in the in your linear algebra package, they sometimes just provide you the eigenvalues and eigenvectors. It would be a function like eig, or you can use something called SVD, singular value decomposition, to find these things. But I'm leaving it out because it simplifies the explanation. Going into that detail would be too much detail for this webinar. After all, we have to come up with some interesting stuff, right? Now, let's see how do we apply these things to faces, these concepts, right? So when we created an eigenvector is basically, it's basically a face, right? It is a face. It's the same dimension as the face. We can find, we can create new faces from the eigenvectors we have created for face image by simply using this formula. And let me explain what this is. So F is a new face, okay? And Fi, this is basically the eigenvector we have found from that analysis, right? We have found, and I'll go over the code so that it becomes very explicit what we are doing. But we have found the eigenvectors from the face data, right? We multiply some alpha. This could be any alpha. So when we multiply different alphas to the eigenvectors, we can create new faces. And this one is the mean face. So remember we had subtracted the mean. We have to add back the mean to get a new face. And let's go over this example, right? Let's go over the code actually. As I said that we had these images of celebrities. Actually, this image, what I did was we had bigger images. We converted them to 100 by 100. And if you look at this image, most of these images would be, maybe it's not 100 by 100. Now I see that it's rectangular, but it is some fixed dimension, right? So we did two things to this. First of all, we ran a facial landmark detector, and we made sure that the eyes are aligned. So if I, let's see if I can change this. Now, if I quickly go over these images, you can see that the eyes don't move, right? The corners of the eyes, they are static, right? For all these images. So that we have done by design, that we actually took all these images, ran a facial landmark detector, and then aligned it such that the eyes don't move, right? The rest of the data can move. Okay, so now let's go back to this. So here we'll use this thing called PCA compute in OpenCV to compute the data, right? So the data that we had created, the images that we have created, right? They could be, let's say they are 100 by 100 images. What we did was we strung out the image into a vector. Like I was saying that take any facial image, crop it to a particular size, and then string out the vector. You have a matrix of 100 by 100 by 3. 3 is for the channels. And you string it out. And basically you unroll the matrix into one long vector. These are just numbers, right? You can simply do that. And that becomes your vector that we are going to give to this PCA thing, right? And conveniently, OpenCV does allow you to compute the principal components of the data. And this data matrix is basically the matrix that you create by loading all the images. Let me actually bring up a Jupyter notebook that will make it easier to understand. Sorry. Okay. So here we are reading all the images, right? In this example, is it big enough for people to see?
I can read it, yeah. Okay. One quick question from the audience here about the faces, the facial images. Could you briefly talk about why we made sure to align the eyes?
Yes, so if you don't align the eyes, you see we are helping the algorithm, right? We are helping the algorithm. If you don't align the eyes, then it will become very difficult for it to recreate a face, right? We want to, ideally what we could have also done is aligned one more point on the face, but we didn't want to squish the data. So by aligning the eyes, we have made sure that the translation component of the face is gone. The face could move, right? By aligning the eyes, we have made sure that we have something to peg the data onto. We have we are normalizing the data. We are aligning all the data so all the faces line up nicely. Does that make sense?
Yes, I believe so.
Yeah. Otherwise, what would happen is that you would start seeing garbage, because without aligned data, you will just imagine that your data set is, they are in different scales and they are at different location, right? One face could be completely on the side. So when it reconstructs, it could reconstruct a non-face, right? It could reconstruct half of a face and things like that. Here, when we are aligning the data, we are making sure that when it reconstructs the same face. Because ultimately, think about it, that this vector that is representing the face, if it is not aligned, you will see blurry images and things like that, blurry faces and things like that, right? So you'll get a slightly sharper image by aligning the eyes.
Makes sense.
Okay, so here in this code, we are reading the image. Basically, all the images we are reading. We are taking the image and dividing it by 255 and converting it to float 32 as well, right? Oh, there is one other trick that we are doing here, just to increase the size of the data. Remember that we have 200 images, and 200 images is not a lot, right? So we are taking that image and flipping it because whatever image we have, the mirror reflection of that image is also a valid face. So why not use that data? It is almost like data augmentation we use in deep learning applications. So we are flipping that image and also passing it to this, right? And then we get the number of images, etc. So this is simply reading all the files from that directory that I showed you, right? The next step is to create the data matrix. And as I said, in this data matrix, we want to make sure that all the columns represent one image. One column represents one image. And here, we basically create a data matrix, which is the number of images, right, which is n. And the columns are basically the size of the image, size 1, size 2, which is the width and the height, and then the color, right? So we are using a long vector to store the image. And then we loop over this, and we basically add everything to the data vector, data matrix, right? So
I love that there's a function just called create new face. For some reason, that tickles me.
Right. Okay. So after this, the main thing here is that we simply, if you look at the main, we will come to create new face. But if you look at the main function, we basically are doing a PCA computation on the data, right? We are passing it the mean, and we are also passing the maximum number of components that we want to generate from this, right? So it will give you, if you don't pass in the mean, it will give you the output, the mean, as well as the eigenvectors, right? Now, I can ask this question to the audience. What is the maximum number of components that this can have? Let's say the images are 100 by 100 by 3, right? What is the maximum number of principal components we can have for this data? Any answers?
I see somebody gave us the formula there, which would be 100 times 100 times 3.
Yeah,
Is that
that's
correct?
right. Yeah, because you cannot have additional, your data was already in this higher dimensional space, and all you're doing with PCA is you're rotating the space so that it is aligned along the dimension of maximum variance, right? That's all it is doing. So the number of dimensions doesn't change. What you could do is, so the maximum number of dimensions you can pass here is basically the size of the length of the vector, right? But you could also pass a smaller number, and the computation is much faster. So when it calls PCA compute, if you say that, oh, I just want 20 components, right? The 20 top components, then the computation will be much faster, right? Otherwise, this can slow down. It can take a very long time, right? So that's what we are doing in the main function. We are basically calling number of Eigen Faces that we want is 10, which means that from this high dimensional space, imagine, right? We are just calculating 10 Eigen Faces. And we will combine these 10 Eigen Faces in different ways to create a new face, right? So that's what all this code is doing here, basically calculating the eigenvectors. Once you have the eigenvector, you can call this function. Now we are ready to go into this function called create new face, right? Here, all we are doing is we have already calculated the eigenvectors or the eigenfaces. First of all, we have to start with the average face. We remove the average or the mean when we are calculating the eigenvectors, but when we want to reconstruct that, it has to be put back in. Otherwise, the data is all shifted. It is not centered, right? So we have to put back that average face. And once you have that, so the output is basically the average face, and then you multiply it by whatever weights you want. So for different kinds of weights, you will get different outputs, and you can create new faces. And as I had mentioned in the very beginning, if you take the best weights, the absolute best weights, you can reconstruct my face.
but only if you take the best ones.
Only the best ones. So let's look at this. It's actually very fascinating to look at the output that we. So here, I mean, if you run the code that we have shared, you will get this interface, and we have both Python and C++ there. Now let's look at what these principal components are giving us, right? This is the thing that I wanted to spend a lot of time on to really understand what this principal component means. So if you let me restart this so that we can start with the average face.
I'm always a big fan of the kind of interfaces for this data where, just adding sliders like that, I feel like gives you a whole lot better understanding of how the underlying structures actually work when you can move them and see the changes happen. Right.
So a question for the audience, what is this face that we are looking at? All the weights are 0. Some people might have already guessed it. This is the average face that you're looking at.
Average face.
Yes. So this is the average face of all the 200 faces that we have in our data, right? And their flipped versions, right? So you can see that this average face is very symmetric. And the reason it is symmetric is that we have not only the face, but also its mirror image in the data. Even if we had not done that, you would see that the average face would have been kind of symmetric, right? Pretty symmetric, because the average of all people, it is symmetric, right? I mean, and it's also in this image, it's not very obvious because we took only 200 images, but the average faces also tend to be very beautiful, right? In fact, they did this thing about. Let me just do this quick Google search for you. Virtual Miss Germany. Okay, so this. Oh God, they don't have this image.
Link rot. The scourge of the internet.
Okay, here. So this person, right, does not exist again. She was created by averaging Miss Germany contestants of a particular year, right? And you can see that she looks attractive, right? She looks very attractive. This person here, she's the one who won the Miss Germany contest in that particular year, and she's also part of this average face, right? But if you show it to people, they would say that this person looks more attractive than any of the contestants, right? So these average faces tend to be very, tend to be attractive because anyways, we can talk about it later. I don't want to spend time on why the average face looks more attractive right now. So you know, if you're dating somebody, you could just tell them that you are so average as a compliment.
Yes, I'm sure that will go
well.
over. They'll go over swimmingly.
Right. Okay. Back to our original problem. So what do these components? We have the average face. Rate 0 is the main principal component. It is the first principal component. Let's see what happens when we change this thing, right? So you can see that the face doesn't change much. It is the background that changes. So in this example, because we included the background, it is the background in those images that has the maximum variance, right? So the background changes from black to white, and that's what it is, right? It is, that's the main principal component. Now let's see what happens when we change the second principal component. You can see that, first of all, if you go to the negative weight, you can see that the hair starts appearing and the person also appears a little darker. And if we go to this side, you can see a blonde hair starts appearing and the person is also lighter skinned.
It kind of looks like Vigo the Carpathian from Ghostbusters 2.
Right. And I'm doing it one at a time because we want to isolate, right, what these components have actually found. So here is another variation, and that's not a surprise either. If you look at the number of pixels that hair takes up in this image, first, background was the maximum variation, and then hair and hair color is the second largest variation. You can do the same thing. Can anybody guess what's going on here?
It's it's rotation, right? It's which side?
Yeah. So first of all, there's the pose. The person is gradually changing the head from one pose to the other. But you can also see that the lighting is changing, right? It's capturing the lighting from one side of the face to the other, right? The thing to note here is that in machine learning, right, as humans, we have certain concepts, and they are very distinct concepts for us. Like background is a concept, hair is a concept, lighting is a concept, and then pose is another concept. And we think about them as distinct concepts. And sometimes we get lucky that the machine also thinks of them as distinct concepts. Like here, the variation is mostly in the background, and here the variation is mostly in the hair. But it doesn't mean that the machine also thinks in those dimensions. We often, when we process data through PCA and other means, you will find these concepts to intertwine, right? So you can see here the lighting concept and the pose concept, they are intertwined in this one principal component, right? So that is more common because the machine doesn't care. It doesn't even know the concepts you have in your head. It may accidentally, or sometimes it may align with the concepts we humans have, but it's not guaranteed, right? Now let's look at this component. Here also it's something to do with hair. We have black hair, and then it turns into blonde. And simultaneously, there is a skin tone change also, because there is a correlation between hair color and skin tone, right? So that's being captured.
Yeah, that makes sense.
This is interesting. You can see this is not just skin tone, it is skin tone. So this one pretty much captures the skin tone and some other effects also, like hair also changes, right? Let's look at this one. This one, I feel that it is capturing the concept of gender to some extent, right? This one is more masculine and also age, right? This person is definitely more feminine than this person. You can see the mustache, etc., coming in, right?
Also getting a little more teeth on the left side of that one too, if you notice.
Oh yeah. You're right. Let's go back. Yeah. So Teeth is also another thing. And like I said, that these concepts, we think about these as different concepts, but for the machine, it doesn't matter. It's seeing correlations in the data, right? Here, again, the lighting is predominant. It's capturing the lighting, the side lighting from one side to the other. And I'm hoping that something would also, okay, this one is another interesting one. It's capturing the tone, the color tone of the picture, right? In addition to other things, right? So here you can see it's an orange warm tone. And here it is kind of, cooler tone. And it's also capturing the glasses. If you look at the face, it is capturing, the glasses as well. Okay, finally it comes here. I was trying to find where is the principal component for lighting. You can see that the lighting is more dominant from the side, right? That's why those components came first. The top and the bottom lighting, usually the lighting is from the top. And so this principal component came much later than the side lighting, because usually you don't see that, oh, the person is lit from the bottom, right? But it's still an important consideration, the lighting from the top and bottom. So this principal component captures that. This is, again, some weird combination. Also notice that, the concepts, as you go into larger and larger number of principal components, the concepts that they capture can become much more complicated, right? Because they are dealing with interactions of various human concepts that we have, right? So that's...
Yeah, in the end, it's our perception is the only important part for stuff like this, right? The computer can do whatever it wants to some degree, but we actually really only care about how it looks to us.
Right. And some of these things could be indistinguishable, right? For example, you could actually insert your face in a cutout of another person and have hair. As a human, you can easily tell that, oh, this is this is kind of fake. But to a computer, it may look like, oh, I don't care. It is this concept of hair that is indistinguishable. To a computer, it may be indistinguishable.
It's just as good for the computer. Yeah.
Yes. The final thing we can go over is how to reconstruct this face. So, as I said, that you could reconstruct any face by changing the principal components, but how do you do it in a systematic way? Suppose I want to reconstruct this image using the principal components that we just found, or using the Eigen Faces that we just found. It's actually very simple. What you do is, here, let me, sorry. Basically, to reconstruct a face, you pass in the image, the original image, and this is basically vector that I had mentioned before. You take the dot product of that vector, and this vector is mean subtracted. You subtract the mean off before sending it over to this function, and you take the dot product of that with the eigenvectors. So you're basically projecting this vector you have onto the various axes, right? And that will give you the weight. And once you have the weight, you can simply add it to the average face, and you can do it for as many principal components as you want to get better and better quality, right? So in this case, maybe 10 principal components were used. So you can see that data was lost, but it still kind of looks like that. Here, I can't remember how many were used, but if you use all the principal components, this is the best reconstruction we can get. It is still not going to be perfect because, ultimately we are combining celebrity pictures to create my photo. So it may not be completely perfect, even if you use all the data available, because it's a reconstruction. But you can see that it comes pretty darn close.
So a couple of quick question about the images being used here. It seems like you could sort of limit the number. I mean, basically, you could control for lighting and stuff like that to change what your principal components end up being, right?
Yeah.
So like you'd end up getting vastly different results with those different weights.
Yeah.
If you had more uniform input images, right?
Yes, yes. And like I said, that the objective, I mean, depending on the application, but the objective should not be to collect uniform images. You want diverse, you want variance in the data, right? So the more variance you have, the better representation it will have, right?
Mm-hmm. Sure. Yeah, that makes sense.
Right. Otherwise, you can imagine that you have a face and you're changing the lighting randomly, right? You have a static face and you're changing the lighting in the scene, and you do the principal component analysis on that image. It will simply capture lighting and no other variation. There is no pose variation, nothing else. It will be able to capture the lighting variation, right?
Mm-hmm. That makes sense. Is there another question from the audience here? Is there a way to like auto tune the principal components to like select for sharpness or clarity in our output image?
Only later, like you could no, I would say that there is no obvious way to do it, right? You can analyze it later once it has been done and see it, right? But you can get much higher quality images if you do more alignment of the image, right? If you align all the facial points, then you can start getting sharper image. And
that was another question too. Is people were asking with regards to the data, if you made sure that your input images were like also like the nose was aligned and stuff like that, you would necessarily, I guess, then get sharper, more clear.
Yeah, you would. Since we are running, we also have the prize question, right? Like always, we have to ask a question that. The time just flew here. So we can do trivia real quick. So if you're joining us for the first time, the way this works is I'm going to ask a trivia question based on the presentation that Satya just gave. The first person to answer the trivia question correctly on my screen in the Zoom chat window will win. Would you like to tell them what they'll win, Satya? Well, we will give away OpenCV for beginners. It is a course that is being produced right now. It will be available in September, and people will win that course and Computer Vision 1, which is a more detailed course. It's a 3 to 4 month course on introductory material in computer vision with a lot of practical applications in there. So you will get both of those if you answer the question first and correctly.
Awesome. So during the presentation, Satya mentioned that we were using a specific number of images, a relatively low number of images. How many? Ooh, you answered before I even finished asking the question. It looks like Chintan Patel was the first one here on my screen. Answer was 200. Congratulations. Cool. We will be in touch after the show to hook you up with OpenCV courses.
Great. Any other questions from the audience?
Yeah. So one of several people asked, instead of the original matrix that includes all faces, would this work if you just used a random matrix? What would happen there? It
will give you a random answer, right? Suppose you use cat stocks. So alignment here is very important, right? It will reconstruct something, right? It will get you. The way it's working is, if alignment is good, then you can reconstruct the same category of things, right? It's learning something. But if it is completely random, you will most likely get completely random images that don't even correlate nicely, right?
Just like some noise, basically, is what you're saying. Yeah.
And it would not be like GANs. Like in GANs, what happens is that suppose you have a few different categories of images. It will, let's say you have cats and dogs, then it tries to sample from the data, right? So you may get cats or dogs or somewhat, in between also. But here you will get very funny looking things, because here we are talking about linear combinations of data. And faces are particularly nice because somebody has already shown that faces do reside. If you linearly combine face, then under different lighting condition, you combine the faces of two different people, it will tend to be a valid face, right? So that somebody has mathematically proven that's true, right?
Mm-hmm. Yeah, let's do one more question. So this was kind of interesting. Somebody was asking about, are you aware of this technique with the UI and stuff being used for, say, missing persons cases and things like this?
So actually, PCA right now they don't use principal component analysis or Eigen Faces for face recognition, but this was one of the first face recognition techniques that was valid, right? I mean, that was used for a very long time. Let's say even in the year 2000, Eigen Faces, Fisher Faces, and these kinds of techniques were pretty popular for face recognition. But now, there are much better techniques based on deep learning. It's still a very good, technique to learn. And principal component analysis itself is a very useful concept. And it's also very intuitive when you see it on images, right? If you just learn, if I had just shown some data vectors to you, that would not be very intuitive. Once you see it on faces, it's so illuminating in that sense.
Yeah, I think it really, because our human brains like seeing stuff that we know about, that we see in our everyday lives. And math is sometimes hard to visualize, but it does definitely make a lot of sense and sort of make stuff stickier if we put a literal human face on it.
Right.
All right. You want to take us home, Satya?
Yeah, thank you so much. Let us know if you want to do these kinds of tutorials more often. We do these when we don't have a guest or some guest has canceled, but we can also schedule them more often if people like it, right? So that is it. Thank you so much for joining. I hope that you had a few concepts cleared, including variance, covariance matrices, principal components, eigenfaces, etc. And we will do more of these if people like it. And thank you so much, Phil, for organizing this.
Yeah, thank you, Satya. I got one more quick parting shot here. Chris in the chat says, "Thanks, Satya. You have a very average face."
Good one. Thank you.
We'll see you all next week.
Thanks. Bye.
Thanks so much for watching this episode of the webinar. Please hit that like button, subscribe, and don't forget to tap the little bell icon to be notified when new episodes drop. This week's episode was brought to you by OpenCV Courses. Visit opencv.org/courses to learn from the experts.